Good morning. My name is Pierre Dersin. I'm the Reliability, Availability and Maintainability Director for Alstom Digital Mobility, based in Paris, France, and also an adjunct professor at Luleå Technology University in Sweden. So the topic today is smart maintenance for smart mobility. We'll start by discussing what smart mobility is. Then why does smart mobility require smart maintenance? Then we'll see it's necessary to go from a single asset view to a complex system view to a fleet view, and we'll end with the opportunities and challenges. Alstom Digital Mobility, in fact, is the part of Alstom that deals with the digital revolution, in particular in signaling, but also in many other systems. And actually, Alstom has evolved over time from being a rail equipment manufacturer to a mobility solutions provider, dealing not only with rail, but also with autonomous buses and even road signaling for autonomous vehicles, and also taking services as part of its portfolios, maintenance. Smart and sustainability and sustainable mobility for tomorrow's cities. As you know, a number of cities around the world have what they call a smart city program. Typical example being Singapore, and that includes not just transportation, but also energy and everything that concerns the life of the urban dweller. There are some challenges that they are confronted with. For instance, the city population growth and the growing concern for ecology implies that the demand for public transport is expected to rise 50% between now and 2050. And today, most urban rail networks are saturated at peak hours. There are knock-on delays, local incidents, has a cascading effect. Switching from one mode of transportation to another is not easy in case of incident. There is a problem in the metro. There are no taxis at that time, or no bicycles, no buses. So the seamless chain that we would like there to be to go from point A to point B is more a dream than a reality today. And of course, there's a sustainability aspect, which also implies optimizing the life cycle cost over the entire lifetime of the assets. So there are three desirable key characteristics that smart mobility should have. Flexibility, meaning the traveler, the passenger, should be able to choose between modes of transportation, the one which fits his needs best. That implies some resilience. Efficiency, that essentially is punctuality, minimal disruption along the route, and seamless integration from door to door between the various modes of transportation. So in fact, when we look at this concept of multimodal transportation, it's best described as a system of systems, terminology that was introduced by the military some years ago, meaning we have different systems which most of the time can operate independently, like the fleet of trains, of buses, of taxis, of bicycles, but they should from time to time coordinate because they have one single client, the passenger in this case. Systems are characterized by 5 properties: geographical distribution, operational and managerial independence, heterogeneity. So you can see that the multimodal transport system fits those criteria, but evolutionary development, they don't stay the same over time, and emergent behavior, that is, some consequences can happen that are not necessarily desirable. For instance, in our case, all the buses are stacked in the same station, while all the taxis are at the other end of the city from where the train failure took place, etc., etc. So the field of study has been developed since the 1980s, but it is yet to have adequate treatment of reliability for these systems. And there's an IEEE working group, which I happen to chair, on that topic. Why does smart mobility require some kind of smart maintenance? Well, traditional maintenance consists, on the one hand, of preventive maintenance, which is systematic, time-based, or mileage-based. So it leads to rigid, fixed maintenance plans. And then you have corrective maintenance, which takes place after the fact, after a failure has occurred, and introduces, of course, randomness. The consequence of that is that the maintenance teams can be sometimes overwhelmed, sometimes idle. The resources, peoples, tools, and parts are dimensioned by averages or by worst case. Spare parts may be in excess or lacking. Asset utilization is definitely far from optimized, and availability is most of the time insufficient. So this kind of maintenance is absolutely not in line with the flexibility requirements of smart mobility we have just described. We need, therefore, another type of maintenance, smart adaptive maintenance. What are the requirements for smart maintenance? Ideally, maintenance must make the assets available when they are needed and achieve that goal cost effectively. When they are needed, it depends on the variable passenger demand. So we need to monitor and anticipate even this demand. To make the assets available, we need therefore to monitor the assets and anticipate the failures. So that leads us to condition-based, or even better, predictive maintenance, with all the tools of PHM, prognostics in health management. But in addition to that, maintenance cannot be managed separately from operations, because operations is the end goal. The trains are there to be operated, not to be maintained. So we need to have a dynamic maintenance of a fleet of assets combined with predictive traffic management. Fortunately, something that can help us is the digital revolution, because it enables us to go from the situation we knew in the past, where everyone worked in silos, there was little communication, information was not accessible, etc., to situations where all these actors are linked together, and we can notify whoever needs it about the health of assets, can manage depot resources in real time, can optimize for global productivity. Digitalization, in sum, enables interaction between different maintenance actors and operations. Now, at Alstom, we started some years ago the platform for condition-based maintenance and prognostics in health management called the Health Hub, and we follow the various steps of the ISO 13374 standard: data manipulation, state detection, health assessment, prognostics, and advisory generation for all the various assets of modern railways. And now, I'd like to really emphasize the fact that when dealing with something like the RUL, the remaining useful life, it's extremely important to be aware that it's a random variable. It can only be described by a confidence interval, for instance, or a probability distribution, and not by a single number. Because there are uncertainties that some of them are inherent to the model, epistemic uncertainties. Some have to do with the data, measurement uncertainties, and some have to do with the future load that the asset will be subjected to. If we don't take these uncertainties into account and have a deterministic view, it's rather meaningless. And in fact, there is a concept of RUL, loss rate per unit of time. Whenever you increment the time by a unit, how much RUL do you lose? And that depends on the characteristics of course, the equipment. If in the limit of deterministic aging, this aging rate is 1. For every hour that goes by, you lose 1 hour of life. But at the other limit, the exponential distribution, you never lose any life. The expected remaining useful life, or the mean residual life, is always the initial MTTF. So for this case, the confidence interval is maximum, and for the deterministic case, it's minimum. So as the aging rate increases, the confidence level, confidence interval shrinks. It can be demonstrated mathematically for a class of distribution, but intuitively, I think it should be true in general. This is just to illustrate the importance of the dealing with uncertainties. Also, another remark along the same line is that typically the way machine learning algorithms work is that they have to be trained on a normal situation, so-called baseline, which in this case is shown by the signal. But as conditions evolve over time, sometimes the baseline has to be reset. Otherwise, one confuses degradations with simple changes in context. So that is also another part of uncertainty, the context evolution. And yet, if railway operators are to trust predictive maintenance, there must be guaranteed performance levels in terms of detection. False alarm rate should be low, detection rate should be high, diagnostics should be correct most of the time, and prognostics should be accurate. And all of that in spite of the multiple uncertainties we have just mentioned. So this is part of the challenge. So Alstom has a number of so-called fleet support centers where data from the vehicles and the infrastructure arrive 24 hours a day, and the data are then processed. So far, we've been talking about the monitoring and the diagnostics and prognostics of a single asset, but we also work with rather complex systems. For instance, the radio communication, which is at the center of operation for communication-based train control, or ETCS. The data communication system is, of course, critical. There are a number of degradations that are linked to the radio signal quality. And when they happen, they lead to disruption in operations and therefore delays. You can have losses or delays of packets, so the train doesn't receive its movement authority on time, and therefore an emergency brake is triggered, which is, of course, a cause of delays. So we are working on monitoring the radio communication and using machine learning algorithms to understand and diagnose kinds of degradations that can take place, so that we can take preventive maintenance measures to avoid the corresponding traffic disruptions. Now, dealing with single assets, dealing with complex systems, but reality is that we have to deal with the maintenance of a complete fleet and to reconcile the needs of maintenance and those of operations. So first of all, there's a fleet planning issue, then workload optimization, and then execution. And this is all linked with the maintenance management system. And this is what we call the dynamic maintenance planning and end-to-end digitalization of operation and maintenance execution. If you think about it, there are some assets that have to be operated and maintained. So operations sends its needs to the maintenance. It says, I need this and this vehicle in order to perform this and that mission. Operations generates the schedules. Assets are more or less available. They also send their health to the maintenance. And so you can look at this as a multi-agent system where there is an agent that is responsible for operations, one which is responsible for maintenance. The two are somewhat conflicting because the maintenance agent would like the train to be in as good a health as possible, but the operations maintenance really wants the train to run. And then there's an agent that is responsible for the resources. So in fact, we have to deal with a decision problem where you have as inputs the various maintenance resources, the rolling stock and the infrastructure, and the health indicators or remaining useful lives that are sent by the various assets being monitored with their uncertainties. There are some operations constraints, that are the missions that have to be fulfilled. There are some performance objectives, and the output of that is the train routes, which trains get to go where, the predictive maintenance planning, which trains get to be maintained when, personnel planning, and also the performance indicators. So we are dealing with an optimization problem under uncertainty. So we have devised a suite of tools that run the whole gamut from fleet planning optimization, planning simulation, to workload optimization, that is once the decision has to be made which vehicle should be should be maintained, and you have to optimize the task sequencer, then execute. All of this is digital, so it's dynamic optimization, but with under uncertainty. Then I'd say a few words about optimization of the operations. This is what we call the master mobility platform, where we have to coordinate various modes of transportation, supervise the operation, and predictive analytics to plan and optimize the mobility based on demand. So, in fact, we use various kinds of data, including ticketing, smartphones, the weight of the trains, which tell us about the number of passengers. And based on that, we can anticipate, analyze people flow, and anticipate the evolution of the demand. We can also monitor and predict the people flow using, in fact, several methods, including deep reinforcement learning, and then we can inform passengers. One example, dramatic result, is the management of the flow in Panama City, where there is what is called a fail-to-board rate. A number of passengers that come from feeder line cannot board the train on the central line. Fail-to-board rate was 50%. And so using passenger flow monitoring, we're able to decide which trains to send to the areas which are most critical, and to cut down the fail-to-board rate from 70% to 40%. So that means 3 minutes less waiting time for 30,000 passengers during peak hours translates to a substantial amount in GDP savings per year. So to conclude, I'd like to share with you this global vision. On the one hand, there's a demand which has to be predicted, and it includes some degree of uncertainty, the passenger demand. On the other hand, you have the supply, and we have to predict the availability of assets based on their health. And that also is fraught with uncertainty at the single item level, complex system level, and then going from the single asset to the fleet, not only for the rail mode, but for other modes as well. So it introduces the dimension of a system of systems. All of that, the goal is to optimize maintenance and operations. So it's optimization under uncertainty, and we can combine traditional methods with AI. So the opportunities are indeed to leverage the AI, and particularly machine learning, combined then with traditional optimization, to perform maintenance which is adaptive to context and also operations policies, to have reconfigure algorithms, learning from past experience. For instance, here learning from past situations how the flow will evolve, and the whole area of deep learning for PHM, which is very promising but still not very mature. Also, to model more explicitly, perhaps the negotiation process between operations and maintenance agents using things like game theoretical approaches. Challenges include large-scale real-time optimization of distributed systems with multiple decision makers, as we saw, operations, maintenance, dealing with systems of systems that naturally arise in a multimodal context, dealing with uncertainty and uncertainty propagation, and optimizing the architectures between, say, centralized architecture where we upload all raw data to the cloud and then process them there, or decentralized architecture where the intelligence is brought down to the assets. And last but not least, cybersecurity and safety must be assured. So a few bibliographical references, tribute to my colleagues, and my details. Thank you very much, and I look forward to questions.